All right, welcome to Chapter 8, Section 2, called Volume of Cones. So the first thing, this is Math 8. The first thing that you'll see on your screen is a due date. I don't see that on my teacher preview, but you will see it on your student screen. The second thing is the number of attempts. So this tells us it's unlimited attempts. We have unlimited attempts on homework, tests, and quizzes, so you can come in and try them as many times as you would like. Number of questions just tells you how many questions we have on this particular assignment. Grading policy is best score, so whichever attempt is the best one is the one you keep. Partial credit is enabled, so if you answer 1 of 5 questions correctly, you get credit for the one question. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. What that means is once I click start, down here in the bottom right corner, I will see a submit assignment button. I want to make sure that I'm clicking that button when I want to leave the screen. So whether I've started these or haven't started anything at all, if I want to leave right now, I need to click that submit assignment button. It does 2 main things. So the first thing, just like that other screen said, is it's going to lock you out of all of your other assignments. Alex will assume if you just close this screen or close your computer, you want to leave this attempt open. Remember, you have unlimited attempts. You don't need to do that. So as long as you have a green check mark, it's not going to start you over. If you don't have any green check marks, if you haven't started anything, it's going to have you look at them all again. But whatever you have a green check mark for, it's going to save that. And it'll stop the system from locking you out. The other big thing it does is it affects the grade book, which means your teacher can actually see what you've been working on. Until you click submit assignment, your account's basically frozen. We cannot see anything you're working on until you click that button. So good habit, always click it. All right, over here we have explanation, example, and message center. So explanation tells you you're going to lose your current question attempt because it's going to give you the answer to this question. So it's not going to give you the answer and then let you come type it in. Sorry, not how this works. Example gives you something very similar to what it is we're looking at. So here's just another rectangular prism, which is just a fancy name for a box. And so it has you looking at this in exactly the same way that this problem is having you look at it. So once you're happy with this example, you can close it. You can open another one if you want to see another one, or you can message your teacher directly from the screen to reach out to them, and it'll attach a picture of this question so we know where to come help you. All right, let's go ahead and get started with this. So I know it's called volume of cones, but we're going to first start with a rectangular prism here. So I had this open on my last, let's see. Nope, that's not what I wanted to look at. I think it's hiding behind here. So we have a rectangular prism. And it's even showing us a rectangular prism there, and it's a nice little thing. On this one, it's a box, right? So we can see this turning around. And we want to pay attention to the idea that it has a net, meaning we can cut it open and we can flatten it out. What would it look like? So we definitely want to kind of picture this box and all of its pieces. How do we calculate what it is they're asking us to calculate? So with this one, it says the figure below shows a rectangular prism and one base of the prism is shaded. So we can see that, right? The bottom here is shaded. We can also see some figures. So I can see that the bottom has a length of 3 and a width of 8, and the entire prism has a height of 6. So it wants us to write an expansion to find the volume of the prism using its length, width, and height, and then simplify. So we have volume of a prism, the length, the width, and the height, just like I just talked through that, right? So now we actually want to do this. 8 times 3 times 6. So let's see. I'm going to do 6 times 8 because that gives me 48. And then times 3, so that's 24, 12, 13, 14. So 144. So you get 144 cubic units. And what that means is if we fill this up with tiny little cubes, and I can even bring this guy over here so I can kind of show you what I'm talking about. Let me grab it. Come on, save it. There it is. Nope, don't save that. All right, so we're going to zoom in on this. So what this means is if I were to divide this up into 3 here, let me do that a little better. 1, 2, 3, like that. So there's cubes. And then this is 6, so here's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We'll divide that up a little nicer. So it's not quite perfect there, but these would continue up, right? And then I would also continue these along the side. because they're cubes. I'm basically like if I could fill it with like little sugar cubes or, you know, the little math counter cubes that we used to use. We used to use those all the time. And then we would also have 8 going along here because this is a length of 8. 1, 2, 3, 4, 5, 6, 7. So 7 lines gives me 8 because 1, 2, 3, 4, 5, 6, 7, 8. There's an 8th one on the end there. So what we're kind of doing is we're picturing this if we could divide it up into cubes. Little tiny, dang it, I can't draw a straight line right now. There we go. Like that, and these would continue over the top. I'm drawing these super crooked. Sorry about that. I'm not doing a very good job of drawing these nice and straight. That looks horrible. It should go more like sideways. Should follow the angle here of this guy, but I'm having trouble picturing it. There we go. That's a little bit better, I think. Whoop, that one went funky. That and like that. All right, so better-ish. Not perfect. So what we're doing literally is just picturing this whole thing is filled up with these teeny tiny little cubes, just like this. So if we could count them all, it would be 144 cubes. But instead of counting them all, that's going to be very, very tedious to sit there and count 144 cubes. I can just go 3 times 8 times 6, and that tells me how many cubes there are. So what they want us to do is focus on find the area of the shaded base, then using the area of the shaded base, write an expression to find the volume of the prism and simplify. So if we just focus on the shaded base, and I'll kind of airbrush this a little bit. So we're just going to focus on these guys down here. How many cubic units are down here? And remember, this is kind of continuing through the whole thing. I know I'm only looking at the one side, so that's not terribly helpful, but we would also have these lines kind of continuing. Blah, I don't want to do that. Continuing through here, like there's layers of cubes going across through here. And I don't know if that helps. I think that's way too many lines to look at, so I'm going to take those away. But we just want to see how many cubes are on the bottom here. If we're just looking at the bottom. Why did that change to the other blue? That's interesting. Like that. So with that one, we simply just say, well, it's length times width. 3 times 8 would give me 24 cubes. Right? And I can count them. I can go, 3 plus 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 3. That would be 24. Or I could go 8 plus 8 plus 8. That would also give me 24. So I could count those if I wanted to, but in this case, we can do the multiplication because that's what they're asking us to do. So 3 times 8, that gives me 24 square units. So I have 24 of them. Each layer, as we go up here, has the same number of units. So this guy would also, so if this is 24 cubes, this is another 24 cubes. The third layer is another 24 cubes. The fourth layer is another 24. And another 24. And another 24. So here's how it's repeated over and over and over again. It's 3 times 8, 3 times 8, 3 times 8. Each layer is another area. So what we can do is we can use the area of the base and multiply that by the height. Instead of saying 24 plus 24 plus 24 plus 24 plus 24 plus 24, woof, that was a lot. Let's just say 24 times 6. So 24 times 6. Why did that go 0? I did not mean to type 0 in there. So 24 times 6, which is actually the same thing as up here. Instead of doing 8 times 6 times 3, which for whatever reason the way I did it, we're doing 3 times 8, which is 24, and then multiplying by 6 to get 144. It's still the same answer. We're just looking at it kind of in a different way there for base times height. And a lot of these formulas, that is how like the basic volume formula works. It's going to be the volume equals the base times the height. And this is whatever the area of whatever shape the bottom is. So if it's a rectangle, it's length times width. If it's a circle, that'd be pi r squared. If it's a triangle, it'd be 1/2 base times the height. And in that case, when I say base again, it means the base of the triangle. So the length of the bottom of the triangle. So again, we need to know kind of how to calculate all these areas. There's a lot going into this when we start doing volume. All right, let's go to the next one here. And I need to scooch this up. I just realized it got scooted down. I don't know why this is all a little wonky today. Oh, I scooted it over to get that picture. That's why. I forgot about that. Okay. So the rectangular prism and the rectangular pyramid shown below have the same length, same width, and same height. So we can see 5, 5, 4, 4, 3, 3. So what we're going to do is we're going to compare these two. And if we, think ahead on this one, and what do we notice? What do we wonder about these guys? Well, I notice that the even though they have the same length, width, and height, this cube or rectangular prism, it's not a cube, sorry, rectangular prism, looks like it's going to be having more volume than the pyramid. If I were to fill this up with liquid, more liquid would fit in here than in the pyramid, because it looks like a lot of area or volume was kind of cut off by coming up to this point here. So I kind of notice, that this one's going to be bigger than this one as far as volume goes. So let's go ahead and compare them. Let's go. No. Let's not save that diagram. All right. So now we have the volume of the prism. So remember, that's length times width times height, or base times height. This could also be base times height. Same idea. So length times width, that's 20. 5 times 4 is 20, times the height, which is 3. So 2, 4, 6, that's 60 yards cubed. And I kind of did that a little bit out loud instead of writing every piece down. But the base is length times width. That's where I got 20. 4 times 5. And the height is 3. So 20 times 3 gives us 60. So the volume of the prism there is 60 yards cubed. Let's do the volume of the pyramid. Now this one's a little bit tricky because we need to make sure that we know how to find the volume of a pyramid. It's not just length times width times height. So if you click on here, and I believe it's always going to be rectangular prism and pyramid, because so far that's what I've been seeing. With this one, it's still base times height, but we need to divide it by 3 or multiply by 1/3. So it's still very similar as far as base times height. And because the bottom of a rectangular pyramid is rectangular, that's where the rectangle word comes from, it's still length times width for the base. And then we're going to multiply by the height. So we get this same answer, length times width times height, but we have to do times 1/3. This. So it's still 1/3 base times height. All of this stays the same. And the 20 times 3, because it's still length times width. 20 times 4 times 5 is 20. Height is 3. So we get 1/3 times 60. So now 1/3 times 60, what this means is I'm dividing by 3. I want to know what 1/3 of 60 is, or 60 divided by 3. So I'd go 20. I can also look at this before I multiply and say 1/3 times 3. Well, these guys would have canceled out, and the 20 is left behind. So this is 20 yards cubed. So looking at this one, I could definitely tell, I can see visually that the rectangular prism was going to be bigger than the pyramid. And now I can see, mathematically, yep, the prism is bigger than the pyramid. So now it says the volume of the prism equals blank times the volume of the pyramid. So we want to focus in on this piece here, this 1/3. So if I'm thinking of the prism is 3 times the size of the pyramid. I'd have to multiply the pyramid by 3 to get back to 60. 3 times 20 gives me the 60. So the prism is 3 times the volume of the pyramid. So this equation is true only for rectangular prism and rectangular pyramid shown above. So it wouldn't work for other ones, is what that says. This equation is true for all rectangular prisms and rectangular pyramids. This equation is true for all rectangular prisms and pyramids with the same length, the same width, and the same height. So that's a very important distinction there. It wouldn't be true for all rectangular prisms and all rectangular pyramids, because they could have different lengths, widths, and heights. And then this situation where I have this either canceling or, having this very specific relationship where it's 1/3 of the prism to the pyramid, wouldn't work. It has to be the same length, width, and height. So they have to have those pieces the same. The only difference is that one is a pyramid and one is a prism. Okay? So that's, you know, one of those pieces. We want to compare that. But it's the exact same formula. We're just dividing by 3. So again, if I were to fill liquid up into the pyramid and pour it into the prism, it would take me 3 times to fill up the prism from the pyramid. Kind of another way to think about that. All right, so now we're actually going to get into cones, which is the namesake for this unit or this section. So find the volume of a cone with a height of 7 centimeters and a base diameter of 6 centimeters. Use the value 3.14 for pi. Do not do any rounding. So make sure you're paying attention to those directions. Don't round if it tells you not to round, okay? So now finding the volume of a cone, again, we need to know what's the volume of a cone. And this is, I believe they're going to do this on number 4, but this is comparable if we have a cylinder like this and we have a cone. And if we have a cylinder that's the same height, the same radius or diameter on the bottom, if they're comparable like this, it's the same mathematical properties that we just saw in a pyramid and a prism. It's going to be 1/3 of the volume. So if we know how to calculate the volume of a cylinder, which we did on section 1, that's volume equals pi r squared h, or base times height, because this is the base area. That's how you find the area of a circle, is pi r squared. So it's still that base times height. That's a very common property here. But what we're going to do for the cone is it's going to be 1/3 pi r squared h. We're going to divide it by 3, which is the 1/3 base times height. It's the same idea that we just did with the prism and the, click on the wrong one here. So if you look through here, it's going to show us that same idea. It doesn't relate them for you on this one. I believe we're going to do that on the next problem. So it's kind of getting a jump on that next problem a little bit, seeing that relation. So find the volume of the cone with the height. So we have 7. So we're going to fill this in because base, we want to make sure we know how to find the base area. So it's 1/3 times 3.14. That's what they asked us to use. Times radius. They told us that the diameter is 6. Now, if we're thinking about a circle, a radius goes from the center to the side. A diameter goes from side to side through the center. Well, if a radius goes from the center to the side, these are just 2 radii. That's all a diameter is, okay? So we're going to take that 6 and divide by 2. So we get 3 for the radius. And then the height is 7. So I have my pieces for my volume. I need to go through and I need to do this. Now I can do that same thing I did on that last one where we have 1/3 times 3. Those will cancel. If you don't see that right away, that's fine. I would go through and type in the rest of this first. I'll just go ahead and leave the 3 in there like this. So I'd go through and do all this first and then divide by 3 to do the 1/3 instead of trying to type 1/3 in. Although this calculator is actually pretty good. I can do 1 divided by 3 and then times 3.14 times 3 times 7. So I can actually do the 1/3 on this calculator pretty darn easily. So not a big deal on this one. Some calculators that you can't type it in quite the same way. But using the Alex calculator, it lets us do that. So this is the volume of this cone, 21.98. And we need to make sure to include our unit. They're not doing that. Remember, this is a volume. That means 3-dimensional, length, width, and height. So I need to go cube. I need to see that little 3 there. That tells me I'm using 3 dimensions. Uh-oh. Did I multiply something incorrectly? Do not do any rounding. I didn't. 1/3 2.14 times 3 times 7 What is it not like? Oh, dang it, I forgot to square it. Silly me. This should be pi r squared. Goodness, goodness. So it wouldn't actually completely cancel out, would it? Jeez Louise. Me messing something silly like that up. Does everybody make mistakes? Of course they do. We just go back and we fix what it is we forgot. Oh, dang it. That's not where I wanted the times symbol. Right there. Times 3 squared times 7. Now it'll be the right number. So now it's 65.94. 65.94. So darn it, I'd forgotten to square that because I was focused on the 1/3 there in my explanation and totally forgot to include the square when I brought it down here. So don't forget that part. Definitely very important because that would leave off one of our lengths. That's kind of the idea of length and width right there when we square the 3 for the radius. All right, so just like I thought, we're going to compare a cone with a cylinder because those are comparable, just like a prism and a pyramid are comparable. As long as we have the same base shape, generally we can compare these two items. So if you notice, they have congruent bases and equal heights, so they're giving us the base area. They're not even telling us what the radius or diameter are. They're just saying this one has 13 centimeters squared and this one has 13 centimeters squared. Remember, it would be pi r squared to do either one, so that means that the radius would have had to be the same if we're simply just doing this pi r squared to get 13 centimeters squared for both. So they simplified it for us a little bit. We're going to do the volume of the cone. So we have 13 base times the height, which is 6. So let's see, we would get 18, 6, 7, so 78. So we get 78 for that guy. And then for the cylinder, same thing, it's going to be base times height. So 13 times 6. Oh, what did I forget to do on the cone? Ha ha ha, I forgot to divide by 3, didn't I? This guy's going to be 78, but the cone is 1/3 of that. I have to divide it by 3 because we're shedding off a lot of that space there when we come to this point. So I have to make sure I divide by 3, and let's see, I would get 2, that would be 1 left over, and I would get 6. So I would get 26. And I could have also done that here because it would have been 1/3 times 13 times 6, so I could have canceled the 1/3 on the 6 because 6 divided by 3 is 2. And now 13 times 2 is 26. Either way, doesn't really matter when you do the canceling there. All right, so we can definitely see that it's 1/3, or it's 3 times the cone for the cylinder. So this equation is true only for the cylinder cone shown above? Nope, it's definitely true for every single cylinder and cone as long as they have the same base area and equal heights. It could also just be same radius or same diameter and heights, because if they had the same radius or diameter, their areas would be the same on the base because you calculated exactly the same way. All right, come on. All right, we are going to go to the last one here. So a company uses paper cups shaped like cones for its water cooler. Each cup has a height of 10 centimeters and a base diameter of 12 centimeters. So we have this paper cup here, something like this. And this is kind of a common one, you know, where you get the little cone cup. And it has a height. So I'll go height on the side here, 10 centimeters. And it has a radius. Nope, sorry, diameter. I said radius already and I corrected myself and then corrected myself again. So the diameter is 12 centimeters. The cooler has 16,956 centimeters cubed of water in it. how many cups can be filled from the cooler? All right, so they're not asking us to find volume, but we need to find volume to answer the question. So I need to know how much can each cup hold. If I filled it up to the tippy top brim of each one of these cups, how much can each cup hold? So then I can use that to divide into this to figure out how many cups can it fill. But I need to know how much is in each cup first. So I need to know the volume. So again, just be aware, pay attention to what it's asking you to find. So with this one, I want to do 1/3 base times height. So the base is pi r squared, and even though it's on the top here, we still consider that the base. We don't consider this vertex point the base. The base is the circle. So we have 1/3 times pi r squared times height. So 1/3 times, and they're asking us to use 3.14. 3.14 times the radius. Remember, this is radius and this is radius. Radius just means goes from center to the side. Center to the side. So if there's 2 radii and all radii in one circle are equal to each other, they all go from the center to the side and they're equidistant from the side. That's the definition of a circle. So we can just say 12 divided by 2 gets us our radius. So that's going to be 6 squared times the height of the cup, which is 10. So now I'm going to go 1 divided by 3 times, nope, get out of there, times 3.14 times 6 squared, don't forget the squared like I did last time, times 10. All right, so each cup can hold 367 and 8/10 centimeters cubed. So this is each cup. This is not my answer. That's not how many cups I'm using, right? So now I need to go and I need to take this number here and I need to divide this number by how much each cup holds. This is how much the total water tank holds. This is each cup. So if I divide, number one, the units are going to cancel out because they're the same unit. And I'm going to just know the number of cups it's going to take. So I can kind of cheat on here and go to the beginning and start typing this in instead of having to type in both and click divided by. Oh man, it didn't work the way it was supposed to. We'll copy, cut, and paste. There we go. So if you don't know some of those copy paste rules, it's definitely very cool to learn. So you can always look up that kind of stuff, what I just did there with copying and pasting, but you can always type it in too. All right, so 45 cups and the water tank would be empty, or the water cooler would be empty. So let's go ahead and click check, and we are good to go. All right, I will see you in section 3.